pretty quick. Okay? So number one, a book is at rest on a tabletop. Diagram the force acting the books. Okay, we're at rest on a tabletop, right? And this was the thing that always bothered Stefan. So we would have weight force and normal force. Okay, so it's at rest on a tabletop. You have the weight force and you have the normal force. Number two. I'll start with me, Goodmanson. Number two, a girl is suspended motionless from a bar which hangs from the ceiling by 2 ropes. Diagram the forces acting on the girl. Now I know the actual answer has weight force, and then because there's 2 ropes, although I don't know about that, she also has 2 arms. What they have is 2 tension forces. If you include them as one altogether, I'm good with that too. You don't need to be. I don't think they need to be separate. So, but I know that's what the actual answer, if I look it up, is. An egg is free falling from a nest in a tree. Neglect air resistance. Diagram the forces acting on the egg as it is falling. Okay, so just like Felix up there in the stratosphere where there's no air resistance, just the weight force. Just the weight force. Number 4, a flying squirrel is gliding, no wing flaps from a tree to the ground at constant velocity. So when they say constant velocity, what they mean is that the forces are equal, exactly. So we got the weight force down, and we've got the, I'll call it a friction force, right? It's air resistance. Now, am I going to get out my ruler to make sure that they're absolutely equal? No, but make them within 2 or 3 millimeters of each other, and we'll have, we'll all call it a day kind of thing. Okay? Don't make them like 2 centimeters longer than the other. Number 5. A rightward force applied to a book in order to move it across a desk with a rightward acceleration. Consider friction. Neglect air resistance. Diagram the forces acting on the book. So we've got a book on a table. We've got the weight force down. There's a rightward force, and it has an acceleration. Consider friction. So it's moving to the right. We have an applied force to the right, and we have a small amount of friction to the left. And do I have is that it? Bradley's shaking his head. No, there's another one, Bradley? There's the one on top, the normal force. Very good. And so the net force is to the right. Correct? Good, good, good. Number 6, a rightward force applied to a book in order to move it across a desk at a constant velocity, so it's almost exactly the same here. We've got a weight force down, got the normal force up, they're balanced. Because it's moving at a constant velocity, that means that the applied force and the friction force are equal. Number 7, a college student rests a backpack upon his shoulder. A backpack is suspended motionless by one strap from one shoulder. Diagram the vertical forces. So it's at rest, so that means the forces must be balanced. And we'll call that applied force. Some textbooks like to call it a tension force because it's, on a strap or something other, but does the labeling matter a whole lot? Not too much. Free bite. Number 8. A skydiver named Felix is descending with a constant velocity. Consider air resistance. Diagram the force acting upon the skydiver. These are getting a little repetitive here, aren't they? Number 9. A force applied to the sled to the right to drag a sled across loosely packed snow with a rightward acceleration. Loosely packed snow is code for friction. There's friction, exactly. Weight force, normal force, but it is accelerating, so I've got a larger acceleration or applied force, and I've got some kind of friction on it. 10 is the one that always causes an argument. A football is moving upwards towards its peak after having been booted by the punter. Diagram the forces acting upon the football as it rises upward towards its peak. Anything else?
Applied force. No, there is no.
That is it. It's already been booted. There is no force applied to it. It's just moving, right? A force is not needed to keep the object moving. Right? So it's just gravity pulling it down. Just gravity. After having been rooted. And at 11, a car is coasting to the right and slowing down. Weight force. It's coasting to the right, so it's moving to the right but slowing down. So all I have is friction that way. Do I have to show some arrow indicating that it's moving to the right? No. Remember, it's not a diagram showing motion, it's a diagram showing forces. So there is no force to the right. Okay, so we did the review on free body diagrams. Today is simply sort of a warm-up on net force kind of things. Oh, I'm zoomed way in here, aren't I? Okay, you probably don't need to write this down, but just a reminder, in the expression F equals ma, the A can be interpreted as the total resultant acceleration which a body receives when acted upon by some total force whose magnitude and direction are given by F. In other words, what I'm really trying to say is that the F in F equals ma is really F net, right? Because it's the net force that actually causes the acceleration, right? It's the net force that actually causes the acceleration. So what that means is we got to calculate the net force before we can go on. How do we calculate net force? Remember, forces are vector quantities. The total force acting upon an object is the vector sum of the separate forces that are acting, and is usually called the net force. So F net is simply F1 plus F2 plus F3 and so on. Is that a formula you need to know? No, it just means add up all the forces, right? That's all it means. Okay, so here's an example. I don't know if you need to jot this one down or not at all. Johnny and Bill, you're playing tug of war. Pardon me? I don't know. Let's have a quick look at it and see. I don't think that it's worthy of writing down, really. Okay? Each one's pulling with 75 newtons, one to the left, one to the right. So this one would be positive 75, that one would be minus 75. You add them together, you get 0, right? Did I add them by vectors? Well, sort of, because this is positive and that's negative. They're collinear, which means they're either in the same direction or exactly opposite. So the net force is 0, so what's that thing going to do?
Not move.
Not move. But only if it wasn't not moving to begin with, right? Exactly. So I don't know, do we need to write that down? It's pretty much common sense. The second one, this time they're pulling on a sled. They're both pulling the same way. Each one pulling with 75 newtons. So what do? You add them together, right? 75 plus 75, net force of 150. I don't think you need to write that. In real situations, friction is often a force that reduces the net force, okay, and it quite often causes problems when we do labs. This results in the formula F net equals FA plus FF, and I hope you remember that from grade 11. Remember that FF, like all forces, is a vector, so it being in the opposite direction will have a negative sign associated with it. So I would prefer that you write F net equals FA plus FF. Generally, if it doesn't say, we're going to assume that our applied force is to the right and our friction force is to the left, making it negative. So don't just write subtract friction. Okay, Courtney? So that doesn't always mean just subtract friction. Okay? I would prefer that you think of it as vector addition. You're adding the applied force and the friction force together. This one you might want to jot down, or at least a simplified version of it. Suppose a 10 kilogram object is being accelerated by a 10 Newton force. The force of friction is 6 newtons. What is the resultant acceleration? We are looking for acceleration. Okay, so just a quick picture here. Weighs 10 kilos. It's being accelerated by a 10 Newton force. Applied force is 10 newtons. Force of friction is 6. Right? What is the resultant acceleration? Troy. I think you're right, yeah. But the number's not really too important. It's how we get there, right? So if I need to find the resultant acceleration, I'm going to end up using F net equals ma. But before I can do that, I need to find F net, right? So you sort of got to work backwards a little bit, right? We're going to write F net is equal to applied force plus friction force The applied force is 10. The friction force is minus 6, giving us a net force of 4. And then I take that net force and I substitute in here. 4 equals, my mass is 10. A equals 4 over 10, or as Troy pointed out, 0.4 meters per second squared. I'm thinking everyone's okay with that. All right, let's expand our knowledge here a little bit. Let's go one step farther. A 3 kilogram object is going 5 meters per second at t is equal to 0. 4 seconds later, it's traveling 2 meters per second. What force of friction is acting? Okay, so there's quite a few numbers in place here. Okay, so we've got an object moving at 5 meters per second, and then over here it's going at 2 meters per second. So it has an initial velocity and it has a final velocity. T equals 0, T equals 4. Alright, so just to clarify here, we've got an object moving already at 5 meters per second. A little bit later it's going 2 meters per second, so friction is slowing it down.
7.
Friction is slowing it down. Now, do I need to worry about, there is a weight force, there is a normal force. Do I need to worry about them at all?
No.
They're balanced out. It's not moving vertically at all. It's a strictly horizontal question. Basically, we can ignore them. Okay? So I need to find the force of friction. I'm likely going to use F net is equal to FA plus FF. Is there an applied force here? Carly, is there an applied force at all in this situation? I think you're just saying that because you're not really paying attention. Do I have an FA written in anywhere? No, I do not.
No,
In fact,
sure.
there is no applied force. In fact, what this means then is that the net force is equal to the friction force.
Next one must have been here. Write that
Okay?
down.
The net force is equal to friction force. So what I really have to do is I have to find the net force, and I'm going to use F net is equal to MA to do that. I have the mass, but do I have the A? I do not. So I'm going to have to find acceleration. So I got to even go back farther. Right? How am I going to get acceleration out of VF, VI, and T? How about, yeah, or this one, which is basically the same thing, right? You don't like that one?
I don't like this white up.
Do you? Yeah, I get all kinds of grade 11s like to do that way, yeah. But with the delta, well, you can write it that way, whatever. I got final velocity of 2, initial velocity of 5, plus A times 4, right? Take the 5 to the other side. You get 2 minus 5 is equal to 4A. Divide both sides by 4. You get minus 3 over 4, or minus 0.75 is our acceleration. And then that goes in place over here. The mass of this thing is 3 minus 0.75. 3 times minus 0.75, I believe it's minus 2.25 newtons. And therefore, and I think you guys know 3 dots in a triangle means therefore, the friction force is also minus, oops, 2.25 newtons. Last one. This time I have a force, but it's applied at an angle. Okay? This
Totally
was
right.
sort of like the hardest kind of one you did in grade 11. We're going to be going a little farther than this. Okay? So I'll give you a second to jot this down. This time the 50 newtons is applied at an angle. I got 50 newtons of applied force. There's a 10 kilogram sled. The angle is 30 degrees, and the force of friction is 18. Now, friction is never going to be, well, I shouldn't say never, but in this case here, the friction is horizontally, right? So does all of that 50 newtons go into pulling it sideways?
No.
No. Okay? When you see something like this, your first indication should be, I'm going to have to find the horizontal component, okay? And so that whole idea about components that we did before is coming back. Okay, right? So I need to find my horizontal component and my vertical component here. Now that vertical component's going to be making a bit of a difference in 2 or 3 more days, but for today we're just going to sort of ignore the vertical component. Or I've written the question such that we don't need to worry about it. So in other words, the first step is to find the horizontal component, FH. Okay? Now the FH is opposite or adjacent to the 30 degrees? It's adjacent. Okay, so I'm going to use cosine. So it's going to be 50 cos 30. 50 cos 30. Do I have it here? I know. Justin, can you do it for me? Oh, that's fine. 43.3. So of the 50 newtons, 43.3 newtons goes into moving it sideways. Now I've got my horizontal component here. I've got my friction force backwards at minus 18. The net force is the combination of those two. So the net force is the applied force plus the friction force. I guess maybe I shouldn't say applied force. In this case, I guess it's the horizontal component. So that's going to be 43.3 minus 18. $25.3. Now that I've got the net force, then I can find the acceleration. What's the mass here? 10. In other words, divide by 10. 2.53 meters per second squared is my acceleration. And then I just asked you, what's the displacement after 4 seconds? I'm just going to do it on this, on here. I want to know what's the displacement after 4 seconds. Okay? What's the displacement after 4 seconds? How far does it go in 4 seconds? Do I need to do it two-step? Use the new one. VIT plus 1/2 AT squared. By the way, like all of the stuff that we did last unit is going to be in this upcoming unit and more. It'll be like new and improved. It's almost like a retest.
Not really. Like both of them count. I think it's close.
Almost like a retest. I might be able to be talked into some sort of deal that works good for all of us. You guys are obsessed with pizza cards. The initial velocity is 0. 1/2 of 2.53. The time is 4 seconds. So 0.5 times 2.53 times 16. 20.24. That is all.